It's a great pleasure to be here, and I would like to thank the organizers for inviting me to give this popular science talk. And I thought, even though I work in different area, I also work a little bit on minimal surfaces, so I thought that may be a better topic to talk on. So what are minimal surfaces? Before that, I will go into what are surfaces, their topology and geometry, and then I will go on to minimal surfaces like soap films, soap bubbles, and so on. So you may have heard about spheres, torus, double torus. You may have heard these names. So this is a sphere, and you see it like glass ball or something. You have seen the sphere, and what you notice, it's very symmetric. And whereas an ellipsoid and an egg, they are not so symmetric, though they have symmetries, but they are not so symmetric. And a torus, you have seen it as a donut or a vada. And what you notice is there's a hole through it. It's like a bangle. There's a hole through it, right? And also you have seen this triple torus. There are 3 holes now, and you have seen it in pretzels and various other objects in nature. Okay, so what's going on? So this picture actually tells you a little more about what's going on. If you have a sphere and you add some handles to it, the surface of that sphere is a surface, and the number of handles you add is called the genus. For example, the sphere had no genus. There were no handles attached to it. Then the torus, there is 1 handle attached to it, because the torus, you can think of it as a sphere. You remove 2 discs from it, and you can add a handle. And then if you can think of it being made with some plasticine or something, and you can deform this part to be one part of the vada, and this part to be the other part of the vada. So if you are allowed to continuously deform without tearing, then this will be equivalent to, this is actually a sphere with 1 handle. Similarly, a sphere with 2 handles is a double torus, right? This is like a double torus. And this was the torus. So these are examples to keep in mind. And you can imagine we can continue to add handles. And so the sphere genus 0 is not topologically equivalent to the torus. You cannot deform continuously the sphere into a torus. Once you have added a handle, its topology has changed. Okay? And which is again not topologically equivalent to the double torus, and so on. So you can see this number of handles you add, or rather the genus, is a very important object. And supposing I give you a very complicated figure, a long thread, I knot it in many ways and I attach it. And then I link it with something else. How would you ever know what is the genus, what is its topology type? How would you know? Well, Euler's formula gives you one way of determining that. You just divide it up into a certain number of vertices and faces and edges. So for example, this figure. You must have seen this figure. This is the tetrahedron, right? And actually it's topologically equivalent to the sphere. But it has been broken, the sphere has somehow been broken into 1, 2, 3, 4 faces. Faces should not have holes in them. Faces and 4 faces and 1, 2, 3, 4 edges. Number of vertices is 4. Number of faces is 4 and the number of edges is 6, right? So now if you count this, V minus E plus F, this should be 4 minus 6. Oh, did I do it the other way? 1, 2, 3, 4 vertices. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 edges. V minus E plus F. It should be plus 2. Yeah, it's coming plus 2, sorry. 8 minus 6 is plus 2. Yeah. So, and Euler's formula says V minus E plus F is equal to 2 minus 2G. So if it is plus 2, then the genus must be 0, which makes sense, right? So let's calculate. You can also triangulate it. I have shown another triangulation. It's like the tetrahedron, but I have retained the spherical nature. So this is one face, this is another, that is another, that is another. 4 faces, 4 vertices, and 6 edges. So again, it adds up to. And you can imagine all the polyhedrons, all the Platonic solids to be representations of the sphere. And one exercise would be you can do V minus E plus F for all of them. This is also a face. This pentagon is also a face. Pentagonal triangle. This is a pentagonal, division. And this is a square division. Whatever it is, this is a triangulation. So whatever it is, however much, in fact, you can even refine your subdivision, doesn't matter. You will also always get V minus E plus F equals to 2, okay? For all these polyhedrons, you can go back and look at the Platonic solids and count them, okay? And what about the torus? Let's count the torus. So for counting, let's show the Euler's formula for the torus. For that, we need to show how a torus is formed from a square. So supposing you have a square or a rectangle, okay, rectangular piece of paper. I identify this side to this side, so it becomes a cylinder, right? I just fold it. I'm just talking about the surface, right? I'm not talking about the inside what's going on. So I just identify these two, so that becomes a cylinder with this line, and then I identify these two. So I identify these two, and that gives me a torus, okay? So what I would like to therefore do is show the triangulation in this picture. So what you see is once you get it down in one more time, get this identification done, it becomes the torus. So, and to get back this, what you can think of is cut it along this and cut it along that. You will get back this. So there is a one way of going from one to the other. Yeah? I will explain this. So you cut it along this, it becomes a cylinder. Then you cut it along this, it becomes a flat rectangle. Right? Got it? Okay. So now, when you cut it along this part divides into 2 sides. And when you cut it along this part becomes 2 sides. And what about this point? Where does it go? Can someone tell me? This point P over here. Can everyone see me? It's too small, or can everyone see this picture? Everybody understood? Yeah, so where does this point go? Yeah, all the 4 corners actually go to that point, right? So let me call it 1, 1, 1, 1. We got 1 vertex. Okay. And now you can see, I will go back to this. So this is the second vertex which has been identified here. The third vertex which have been identified there. Okay. So this edge is actually the same as this 1, 3 edge is actually nothing but this 1, 3 edge. And this 3, 4 edge is nothing but, 3, 1 edge is nothing but the 3, 1 edge. So you shouldn't count them twice. When you do V minus E plus F, you shouldn't count them twice. So let's see how many vertices are there. So for the torus, in this diagram over here, the number of vertices is, there is one in the middle that has not been identified with anything. But one over here, all the 4 points on the torus become just 1 point, right? And this one and this one is 1 and this one is this one. So how many vertices? 4, because there is one in the middle which can't be, which has not been identified with anything. It's somewhere plump in the middle of the torus, okay? And now, how many edges are there? How many edges are there? 1, 3, which is also here. So 1, 3, 3, 1, 1, 2, 2, 1. We can't count them twice, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10, 11, 12. So number of edges you can count is 12. And number of faces, do you agree with the number 12? See, there are 8 faces in the middle which we have not identified with anything. 1, 2, 3, 4, 5, 6, 7, 8. And then this one, this one, this one and this one. So 8 plus 4, 12 faces, 12 edges and faces 1, 2, 3, 4, 5, 6, 7, 8. Faces have not been identified. Just think about this. So what do we get? 4 minus 12 plus 8 is 0. So 2 minus 2j is 0. So the genus according to this is 1. Any questions about this? This kind of construction is very useful because from a sheet of paper you can construct the torus by just a diagram. Remember, only the lines, the edges are being identified. There's no identification in the interior. Okay? Any questions about this? Okay. Then you can any planar figure, what will be V minus E plus F? Any planar figure, you can just take a triangle. So V is 3, E is 3 and F is 1. So Euler characteristic, which we actually denote by chi, is 1. Okay. So you can check if you subdivide it further, nothing changes. It will always remain 1 if it is a planar figure. That's the amazing part. So basically you are telling about the topology through some triangulations or breaking up into faces, you can tell the topology. Okay. So that is one. Okay. Those were oriented surfaces in the sense that you could define the normal and the tangent. So supposing you had a torus, nice, I draw a nice smooth torus. At a point, you can think of a tangent plane. Like it's a plane which touches it exactly at one point. And perpendicular to that is a normal. Maybe I'll draw it here. N. Okay. If you can define a normal everywhere nicely, then it's orientable. But if you take, for example, the Mobius strip, you can try this. You can try this. This is not orientable because you cannot define the normal fully. See, if you take an outward normal, you go right round, it becomes an inner normal. So at a point, you won't be able to define a normal. Okay. So this is an example of a non-oriented surface with a boundary. And can you guess what is the boundary of the Mobius strip? Eh? No, yeah, one what? One circle, exactly. One circle which kind of, so you can go home, take a wire, and twist it, and what you can try to do is, if you dip it into some soap solution, you will see a Mobius strip. I will come to that later. Okay. So the boundary is a circle, but it has been twisted. Okay. See, if you talk about a band, you would think this is a band, right? How many boundaries does it have? 2, right? Whereas this one, just one boundary. You can just, the boundary is a connected, I don't know whether you have gone through connectedness, but the boundary is connected. Okay? So only one component of the boundary is there, and you can construct a Mobius strip. Of course, you can construct it with paper, but I just told you another way of constructing it. You make a wire of the shape of that circle. Take a circle, bend it, and put it into soap solution, you will get a Mobius strip. We'll come to that. Okay, now, so far we have been just talking about topology, where you can continuously deform, and it's still topologically equivalent to the previous one. But when we talk about geometry, we talk of different things. We talk of lengths of curves on surfaces, area of the surface, Gaussian curvature, mean curvature, and so on. So this is what I am heading at today, the geometry. For example, a sphere and an ellipsoid, they are topologically equivalent, but geometrically they are very different. Because, for example, the sphere is totally symmetric, okay, and the ellipsoid is not. This is already a point of difference, okay. Okay, now, before going into this, I want to explain how we characterize curves and surfaces. In geometry, so supposing you have a curve in R3. All of you have come across R3, right? Okay, great. So now you have a curve there. You can imagine it's not a planar curve. Though I have drawn it on the board, it can go here, there, right? Okay. So how does one characterize it? One characterizes it by a parameter. Let me draw it like this. Alpha S is alpha 1S, alpha 2S, alpha 3S. Here are 3 numbers. They belong to R3. So every point here, say alpha, some point here is denoted as alpha at S0. So there is a free parameter S, okay, and you see that gives you one-dimensional figure. Even though there are 3 coordinates at each point, there is only 1 degree of freedom. So actually it traces out a curve. There is only 1 degree of freedom, the S parameter varies. Okay, as soon as you specify S, a point on the curve is fixed. Any questions about this? You can parameterize it by time, you can parameterize it by its length from a particular point. It depends. Your parameter could be anything actually, anything sensible. Okay, but you can parameterize a curve like this. What about a surface? A surface, can you imagine in a surface in R3? How many parameters do I need? 2, right? So x of uv. So there will be x coordinate, or maybe I'll write x coordinate, y coordinate, and z coordinate. You need 2 degrees of freedom, right? So 2 parameters are needed. If you want to just remain on the surface, you need 2 parameters. So, for example, any point here, you give some value to the parameters, it will give you a point here. Okay. There is a small problem. You cannot always globally find the two parameters. It can be only a local picture most of the time. I won't go very much in details right now about that, but later on I'll tell you. Okay, so this is what I mean when I say x of uv is a surface in R3 parameterized by two parameters, x of uv, y of uv, z of uv locally. For example, this surface, let me show you the picture first. This surface, like a spiral staircase, will be very important to us. And let me delve a little bit on this. So you take a helix and there will be a surface spanning it. What is the property of the helix? If you go right round, it climbs a certain distance. You go right round, it climbs a certain distance like that. Okay. So one way of parameterizing it is z is equal to tan inverse y by x. That means your x, y, tan inverse y by x. This is a way to parameterize this. There is another way of parameterizing it. X you can write as r cosine theta, y as r sine theta, and z as, theta. Very good. Z as just theta. Okay. So that's another way of parameterizing it. So parameterization is not unique. Here the two parameters were what? X and y. Everything was in terms of x and y. Here the parameters are in terms of r and theta. So parameterization is not unique. Okay. So let me write it here. Here the same surface is parameterized by r and theta. Here the same surface is parameterized by x and y. Okay. So that's my helicoid. Later on, what we will introduce a novel parameterization. This surface turns out to be a minimal surface. And for that reason, it has a very novel parameterization, which we will come to later. Okay. So what about the normal and the tangent to a regular surface at a point on the surface? Supposing I take a point P, I can think of a tangent plane, a plane which touches it exactly at that point. At P, I can think of a tangent plane which touches it exactly there at that point P. And you can take the orthogonal, the perpendicular line to that plane, call it N. Okay. So that is called the tangent plane and it's denoted by TPS. S is the surface. Okay. And P is the point on which you want to discuss the tangent plane. Okay. And so TPS is the tangent plane to the surface at the point P and N is the normal. Okay. So, and do you know about cross products? Huh? So now supposing, this I should explain very well. Please pay attention to this. So supposing your surface is given locally like this. X of uv, y of uv, z of uv. Okay. So now you take partial derivative of every coordinate. xu, yu, zu at uv. I'm skipping the uv part. And xv, yv, zv. Now what are these? These are two vectors. If you evaluate it at some uv, these become two vectors in R3. It turns out that these two vectors are linearly independent. If the surface is regular, there is some definition of regularity. But you can even take this to be the definition of regularity, that these two vectors are not proportional to each other. So they span a plane. And guess what that plane is? The tangent plane, exactly. So TPS is span of XU and XV. I'll write it like this. So this is span of XU and XV. Okay. So these, the first derivatives are already appearing in the tangent plane. The two partial derivatives, and then you can guess what the normal is going to be. The normal is going to be perpendicular to these two. So here is my surface, here is my tangent plane, here is XU, here is XV. They need not be orthogonal, by the way. They are just linearly independent. Okay, and you can think of the normal. How will you, in terms of XU, XV, what will they be? Cross product, right? But you would like to consider the unit normal. That comes up very nicely. It's called the Gauss map and all that. So I'll just normalize it. So it's XU cross XV, cross product, that gives you something perpendicular to the plane. And you just normalize it so that the norm is 1. Okay. Any questions so far? I would be very happy to explain this again. No, that is the definition of the regularity. They are not allowed to be proportional to each other. That is the definition of a regular surface. Most of these surfaces I told you, they'll be regular. You could define a tangent plane this way. Okay. Yeah, they'll be linearly dependent, yes. Tangent plane, absolutely. I will come to that. There's a long definition of a regular surface, but you can take this to be equivalent, that these two vectors are linearly independent. Okay, okay, so now what about curvatures? We are interested actually in talking about curvature of this torus and also these curves. Okay, so how do we measure that? For a curve, let's see what is a curve. So remember, for a curve, I have written it as L. L of S is L1S, L2S, L3S. This is a curve in R3. So I can talk about L prime S, which is L prime, L1 prime, L2 prime, L3 prime. Guess what is this? At a particular point, supposing you have L of S naught, L prime S, how should I draw it? Tangent along, exactly, very good. This is L primed at S naught. And if I take one more derivative, guess what? That gives you the curvature. Okay. So if I took one more derivative, let me do it here. That gives you a measure of the curvature. The acceleration. Okay, let's, for the sake of simplicity, let's say that we are parameterizing the curve by its arc length. So I just take a point, fix a point, A naught, and I just parameterize the curve by the length it makes from. So supposing S is arc length. Okay, that is a very standard parameterization. Oh, I see. Sorry. So S is the arc length parameter. And then K of S, of course the curvature is going to vary everywhere. So the curve is actually turning, it's an R3, it's a curve in R3. Okay. The curve is turning and twisting. Ks is plus or minus, it depends on your convention, norm of this. plus or minus the acceleration. So that is the curvature. Okay, now using this fact, we are going to try to define. So now we are on a surface, right? How do I even try to characterize curvature of a surface? So you see there are all possible curves at a point. There are so many curves you can draw. Any direction you can find a curve which is tangent to that direction, right? I take the tangent plane and I try to draw all possible directions. There will be a curve. So what we are going to try to do is single out two special directions, call them principal directions of curvature. Okay, so how does one do that? So I'll explain with this diagram. So here you have the surface and there is a normal. There's a tangent plane. I have not drawn the tangent plane, but there's a normal to it, right? There's a normal to it and you start with any direction. So there is the normal and you start with any direction V and you draw that plane through N and V. N and V, there will be a plane passing. So that will cut the surface in a what is called a curve, which is called a normal section. Okay, you call it the normal section and its curvature. So let's call the normal section to be L of S. You calculate its curvature, characterize it by arc length and calculate its curvature and call that the normal curvature in the direction of V. Okay, we are not done yet. There are so many directions. Every direction is going to give you a normal curvature. So what do we do now? Well, we just let the directions vary, find the maximum, and what we find is this Kn will achieve a maximum and a minimum in two orthogonal directions. There are going to be two special directions. So there are two special directions, call it E1 and E2, where the Kn, so Kn dependent on the direction, and now I am going to try to vary all directions, calculate Kn, and what one finds is there are two orthogonal directions where these directions are on the tangent plane, but there are two orthogonal directions in the tangent plane such that Kn is maximum and minimum. These two directions are called the principal directions of curvature, and K1 and K2 are called principal curvatures. Okay. Out of this K1 and K2, we can construct what is known as the Gaussian curvature, which is K1 times K2, and the mean curvature, which is K1 plus K2. These are the only two curvatures you really need to characterize the surface. K1, K2 and K1 plus K2. Okay. So this is called the Gaussian curvature and this is called the mean curvature. Any questions about this construction? You take a normal section, find its curvature, let it vary over all directions. There will be a maximum and a minimum. And those directions, it turns out, will be perpendicular to each other. Those are the principal directions of curvature. And yeah, any question? Yeah. Yeah, this is a big theory. You have to define what is known as the second fundamental form and show that you can define what is known as a quadratic form and yes, arc length. It doesn't matter. What turns out is, in fact, you can also ask, there are many curves. So given a surface and if you're given a direction, in the tangent plane at that point. There are many curves which are tangent to that. So there are many possibilities, right? But it turns out that this Kn, the normal section is enough actually. If you just take the normal section, it's a planar curve, and that will, you could calculate Kn it's actually independent of the curve you took, which is perpendicular to that. That's a very amazing thing. But for a normal section, it's just exactly Kn. For other sections, if you have other curves which are tangent to that, then its curvature is not exactly Kn, but it will be K cosine theta. For a normal section, this cosine theta is 1. Yeah. Yeah. No, the curve we obtain with the normal section is unique, and its curvature is going to be the normal curvature at that point, in that direction. But what I'm saying is, if you take another curve, which is tangential, that may not be a planar curve. The curvature of that won't exactly coincide with Kn, but you have to multiply by a suitable factor cosine theta. I will, when the discussion session starts, I will discuss more. I'll tell you more about this. Okay. So actually it only depends on a direction, and the Kn, to computation of the Kn actually only depends on a direction. Nothing else. The choice of the curve is immaterial. Okay. So now, how much time do I have? Okay, good. So now I have the torus. Okay. Just to give you a flavor of the two directions, principal directions of curvature. So take a point here. Do you think it's positively curved or negatively curved? Positively curved on this side, because the two principal directions of curvature are pointing in the same direction. So the this is a principal direction of curvature, this is another principal direction of curvature. They are pointing in the same direction. Whereas here there is one curve like this, and the other one, see, there is one which, at this point, there is one principal direction like this, and the other one is like this. So this has negative. If the two principal directions, the principal curves, if they turn opposite from each other, then the Gaussian curvature is negative. If they turn in the same side, then they are positive. For example, if you take a sphere, you take two orthogonal directions. Since it's so symmetric, any two orthogonal directions will be principal directions. So you take two orthogonal directions, and they point in the same, they curve in the same way. So that's why sphere is positively curved. Gaussian curvature of a sphere is positive. Okay. Whereas the torus has both negatively curved. See, here I have tried to draw it. This point, it curves this way and this way. So two opposite directions it curves. Okay. And whereas this one curves in the same direction, the two principal curvatures. So that's why here it's negatively curved, Gaussian curvature is negatively curved, here it's positively curved. Okay. Just to give you a flavor. Okay, now we come to the main part of the talk. I'll skip most of it, but just to give you a flavor, supposing you take a wire frame and you dip it in soap solution, you will see surfaces like this. So today I'm going to talk about, these are called soap films, and I'm going to today talk about these objects and their geometry. Okay. And so now supposing you have two wire frames and you dip it in soap solution, you will get a surface like this. And what is the property of this surface? It's a very beautiful surface called the catenoid. So if you hang a rope, okay, it takes the shape of a catenary, and you revolve that around an axis. So this is a catenary. You revolve a catenary about an axis, you get a catenoid. So this is a catenoidal soap film. And what is their property? Well, remember that I talked about the mean curvature. Mean curvature was K1 plus K2. And for minimal surfaces, this K1 plus K2 is 0. That means the principal directions of curvature, when K1 and K2 are not identically 0, I mean at a point if K1 and K2 are not 0, then they are opposite of each other. K1 is minus K2. Okay. K1 is minus K2, and that means at every point it's like a saddle. One of the principal directions, principal curves curve like this, the other one point like that. So at every point where it's K1 and K2 are not 0, it's a saddle. And umbilical points are where the Gaussian curvature is 0. But you have to be a little cautious. Soap bubbles, for instance, are not minimal surfaces. Why? So K1 plus K2 for a sphere is not 0. In fact, it's a positive number. It depends on your convention, but it's a positive number. And in fact, it is, I think they take it to be equal to 1 for the sphere of radius 1. Okay? So soap bubbles are not minimal surfaces though. They are what are known as constant mean curvature surfaces. There's a big theory behind those also. Okay? But minimal surfaces, I wanted to show you some pictures. Here is the helicoid, the spiral staircase which we discussed a lot about. And this is the catenoid, and believe it or not, there is a relationship between them. I will show in the end what is the relationship. This is the enabler surface of one kind, and this is the enabler surface of another kind. This is a periodic minimal surface. This is also another periodic minimal surface. These are called shark surfaces. I'll also talk about these in a little while. This is a very interesting surface called the Costa surface. Costa surface, topologically, what is it? Topologically, it's nothing but the torus with 3 punctures. Just 3 punctures. And what happens is these punctures open out. And you see there is a genus over there. You can't even make out, but if you rotate it, you will see there's a genus over there, and the 3 punctures have become these 3 ends. Okay. So this is one puncture, this is the other puncture, and this is the other puncture. So there's a genus in there. It's torus with 3 punctures. This is the Costa surface. This is the Riemann staircase. This is multiple genus helicoid. Helicoids can have genus in them. Okay. So these are multiple genus helicoids. And you may ask, why not torus? Why not torus itself? Why can't it be a minimal surface? I won't have time to go into it, but minimal surface in certain parameterization, in certain coordinates, the coordinates themselves have to be what are known as harmonic. For that reason, you cannot have compact minimal surfaces, which are complete. Complete minimal surfaces cannot be compact. So you will always find them non-compact. Okay. So you cannot have a torus as a minimal surface. But torus with 3 punctures, well, I showed you, right? Torus with 3 punctures was this one. Okay. So now, how much time do I have? Okay, great. And this is a periodic minimal surface. It appears in crystallography. Okay, now this is the thing I was telling you. You take a Mobius curve. That means you have a band and you twist it, and So if you dip it in soap solutions, you will find that there is not just one, there are multiple curves you get. Multiple surfaces you get when you dip it in soap solution. You will be able to see many of them. And in general, the answer is, there could even be infinitely many minimal surfaces spanning a curve. Douglas, who got the first Fields Medal, he gave the answer that if you have a wireframe, if you dip it in soap solution, you will always get a minimal surface. Existence of what is known as the Plato's problem. Okay. But Tromba, using bifurcation theory, actually gave answers to how many. You have a wireframe, you dip it in soap solution. Every time you see, if you're lucky, every time you will see a different new minimal surfaces. How many are there, you may ask this question. This turns out to be a very deep theory called bifurcation theory, or actually more generally catastrophe theory. Okay. So I will skip all these details and I will come back to this. So here is the shark's surface, and here is the this is the shark's second surface, and this is the shark's first surface. Now sharks, yeah. It will come back a little later again, that's why I showed it again. But this is the relationship between the helicoid and the catenoid. You see, you can isometrically deform them. Like, geometrically these figures are all the same in the sense that the lengths of curves, there's a map between this one to this one, and from here to here, from here to here, from here to here, and finally from here to here. It preserves lengths, areas, and so on. And you can isometrically deform them so that at every stage it is a minimal surface. So this is one way of relating a helicoid and a catenoid, even though topologically they are very different. Right? Topologically this is very different from that, but geometrically they can be obtained from one to the other. Okay? So the reverse problem is also true. I mean, sometimes surfaces can be obtained from isometric deformation. Okay. And the last thing I wanted to show you was this. So I told you about characterizing a surface using xy coordinates, right? X, y, and z of xy. So now if you take x, y, tan inverse tan hy cot x, okay. This surface locally is nothing but this red one, the shark surface. Shark was the name of the German mathematician who discovered it. So this is the shark surface. And what is this one? We discussed this. What is this one? Do you recognize this? The helicoid, right? This is x, y, tan inverse y by x. This is the helicoid. And what is the relation between them? There is a relation. And there comes Ramanujan. Tan inverse tan hy cot x is summation k goes from minus infinity to infinity, tan inverse y x plus k pi. And what are these tan inverse x plus? So if the height function is tan inverse y by x, you know it's a helicoid. What if the height function is tan inverse y by x plus k pi? What is it? It's just a shifted helicoid. On the x equals to minus k pi, you have placed a helicoid. That is again a minimal surface. And if you sum all of them, k goes from minus infinity to infinity, you get Ramanujan's identity. You get another minimal surface. But the minimal surface equation, I just wanted to show you just the minimal surface equation, the mean curvature zero equation. See? So if you write it as x, y, phi of xy, the z coordinate is phi of xy, then it actually satisfies this very highly nonlinear equation. Okay, highly nonlinear equation. But what you notice in this particular case is, you can if you have a nonlinear equation, two solutions, if you sum them, it need not be a solution, right? But in this case, you see it is true. Sorry. Oh, I'm going back, that's why. Is there a way of going straight back to the end? So anyway, what I was trying to say is, this sum tan inverse tan hy cot x is summation, k goes from minus infinity to infinity, tan inverse y by x plus k pi. Each individual on the right hand side is a minimal surface. If you sum them, you get a number. So that's what is amazing about it. So, and also another point is, see, the helicoid didn't have genus, but this develops a genus. If you sum infinitely many of them, there's a genus which happens. So this is what I wanted to show, that is Ramanujan's identity. This identity was derived by Ramanujan, but it was in disguise. In other ways, other forms, it was also known to Euler. And then Weierstrass, Hadamard. There are various, it comes in various disguises. This identity I'm talking about. Tan inverse tan hy cot x is summation tan inverse y by x plus k. Yeah. No, all helicoids. Yeah, you have to put it in an array and sum it. Yeah, infinite number of helicoids, put it in an array. And if you sum them, sum the height functions, you will get this one. So each one of them contributes. At a point here, sorry. Supposing locally it's a graph, at a point over here, all those sums actually contribute. All those heights contribute to give you a point over, height over here. That's what I mean. Okay, so I will stop here. Any questions or comments, you're most welcome to. Yeah.
In the torus, you said that the K1 and K2 point in opposite direction.
Oh, yeah, not always. So the torus
on the inside surface, yes.
Yeah, in the inside part. Yeah, so here you see the torus, let me try to draw it like this. So here it's positively curved because both the parts curve in this way, right? But here what you notice is one of the principal curves, they curve like this, but the other one, it goes like that, right? Can you see? Like the cycle tire.
But K1 and K2 are maximum and minimum curvatures,
Yes.
right? So, like, what I can visualize is that this curve and this curve would both be maximum in magnitude at least. So, are we considering the direction?
No, we are considering the signs.
Signs, yes.
Signs.
Okay.
For example, here K1 could be 3 and K2 could be -2.
Okay, so we are not considering the magnitude or how much curved it is. We are considering the direction too, like plus or minus.
Yes, exactly.
Okay.
So the Gaussian curvature is K1 times K2. This one is plus, this one is minus at this point. So the Gaussian curvature is negative. In this case, it's -6 at this point. Whereas at this point, supposing K1 is 3, K2 is 2, K1 is 3, K2 is 2, then the Gaussian curvature is K1 times K2 equals to 6.
And what is the significance of finding this K1, K2 Gaussian?
Yeah, so that's a very good question. The thing is, there should be some measure of curvature, right? And for a two-dimensional, for a curve, only one curvature was enough to specify everything. I mean, to describe its geometry, let's say. For the case of, for a surface, you can imagine there should be two parameters which characterize. So if K1, K2 and K1 plus K2, if you know, that's actually enough. K1 times K2, the Gaussian curvature and the mean curvature, that's enough to know the surface. It's actually a very deep theorem. I mean, I can't tell you immediately why these two are sufficient to characterize, and in what sense do we mean by characterizing the geometry of the surface.
Yes, I mean, can the value of Gaussian and this K1 plus K2 give the direction?
Which direction?
The V direction. Like along which direction I'll get the maximum curvature?
Oh, that's a very good question. No, that's another method of finding the directions. You mean the two
directions?
Yes,
yes.
Yeah, no, that's but K1 and K2, if you could find the two directions, it's actually easier to find, it's easy to find K1 and K2.
Yes.
Once you know the directions, but the directions are a bit tough to get. Yeah, so. Actually, I don't know the offhand answer of how to calculate the direction immediately. I mean, to see an object and find what are the two directions, I don't know actually. But once you know the directions, the surface is actually locally can be approximated as K1 x squared plus K2 y squared. If you can align the axis like that, along the two principal directions of curvature, the surface can be approximated by a paraboloid or a hyperboloid. And from there you can read off K1, K2. So that's not so tough. But to calculate find the directions themselves, I don't know. Anybody knows from the audience? I don't know. Calculate the directions.
And ma'am, maybe I missed it out or something. What is the condition for minimal surfaces?
Yeah, for the condition of the minimal surfaces is the two, for example, if you have a saddle, okay. So this, obviously K1 is not equal to minus K2, right? Obviously not. But supposing I dip it further and make it a catenary, sort of, then you can imagine that K1 and K2 will be minus of each other. And K1 is minus of K2, so K1 plus K2 is 0. So the condition is mean curvature is 0. So they actually turn in equal and opposite directions. Like if this is curving this way, this should curve this way, but exactly like symmetrically. That's the condition of the minimum. And to calculate E1, E2, if you are given the parameterization, you can actually calculate it by a lot of us, find the second fundamental form and so on. But I don't know, just visually how to get it, maybe there's a clever trick, I don't know. Yeah.
Mobius strip.
Yes.
You said that if we dip it in a soap solution, we will get a Mobius strip.
Yes.
So if we keep
curve. Mobius curve, if you dip it in soap solution, you might see a Mobius strip.
So that means that our boundary is fixed. The length of string is fixed.
Yes.
So can we prove that we will get Mobius strip through Lagrange equation, like calculus on variations?
Okay, that's a very good question. That's not sure, because what happens is calculus of variations, it's a locally minimizing surface, right? So if you see the area functional, what happens is locally area minimizing, locally area minimizing. So if you draw any function which you want to minimize, see there could be places here which are minimums, extremums, right? So what can happen is, here the minimal surface is sitting, the Mobius strip, but out here there could be another thing which is slightly more area than that, but this could also happen. So that's why in that slide I showed, there could be various shapes. So can I go back? Is there time? Talk after that, yeah.